we're looking at some different kinds of architectures as well. We're looking at constellation approaches for Landsat. So instead of just putting one set of instruments on one big platform, can we kind of break this up into multiple platforms and build a little bit of resiliency into the system so you don't get that one failure that just completely takes you out?
Welcome to another episode of the Mapscaping podcast. My name is Daniel, and this is a podcast for the geospatial community. My guest on the show today is Jeff Masick. He is the Landsat 9 project scientist. And today on the podcast, I want to try and give you a brief overview of the Landsat program, starting with questions like, what is Landsat? What is the mission of the Landsat program? What does it take to get a satellite into orbit? How do we get the data back down to Earth? What happens to the data once it's at Earth? How is it processed? How is the data being used? And what is the Landsat program in general going to look like or might look like in the future? So those are the kinds of questions I want to try and answer for you in this episode. So this is not a deep dive technical episode, but I hope that you find it useful and interesting. Hi Jeff, welcome to the podcast. I'm really excited to talk to you. I remember our pre-interview was absolutely fascinating, so I'm looking forward to this. Today we're going to be talking about Landsat, and I think it would be great if you could just take the time to introduce yourself to the listeners, maybe explain what your role is in the Landsat program as well.
Very happy to be here. My name is Jeff Masick. I'm the Landsat 9 project scientist at NASA Goddard Space Flight Center. And the role of the project scientist in Landsat or any other NASA mission is really to ensure the scientific integrity of the mission. So early on, that means helping to come up with the requirements for the mission. As the mission's being built, it means taking a look at the performance data from the instruments, for example. And then, once we're launched, I get to use the data too, which is really great.
Yeah, so there's a ton to unpack there. What is the mission of Landsat? So you talked about some requirements there, some scientific requirements. What kind of requirements are we talking about? What is the mission?
Sure. So Landsat is our longest lived land remote sensing system in the world. I think a lot of your listeners on Mapscaping probably use Landsat extensively, or at least other satellite systems, which in a way are descended from Landsat. We now have a 50-year archive of Earth's land areas consisting of some 9 million images. It's a joint program between NASA and the U.S. Geological Survey. So NASA builds, launches the series of satellites, and then the USGS archives the data and distributes them to users around the world. The key kind of mission for Landsat, I sort of sum it up by the aphorism that you can't manage what you haven't measured. And so Landsat imagery around the world is used to understand how land environments are changing, whether that's deforestation or changes in agricultural patterns or crop types or glacier retreat, and then hopefully to allow better management of our land environment through time.
So I guess when we think about collecting data that are going to help us achieve that mission that you're talking about, I guess there's a lot of different data we could collect. How do you decide which spectral bands are of interest to achieve this?
So Landsat is really there's sort of a trio of parameters that kind of define the utility of Landsat. The spatial resolution, we collect data at about 30 meters per pixel on the ground. That's about the size of a baseball diamond. That's not obviously the highest resolution kind of satellite data that's out there, but it does allow us to get routine global coverage every 16 days from one satellite or every 8 days with a constellation of two. And that temporal repeat is really critical for looking at how vegetation evolves during the growing season and getting enough data so you can compare from one year to another. In terms of what you just asked, the spectral coverage, we're kind of unique in that we cover from the visible wavelengths that our eyes can see out into the infrared, including out into the thermal infrared, which is basically sensitive to Earth's surface temperature. So we get the color of the reflected light off the surface of the Earth, and we also get the Earth's temperature.
So I realize resolution isn't always the best proxy for the quality of the data that's being collected, but does it play any kind of role in terms of how much data we can collect and perhaps the continuous collection of data?
Well, in general, the higher the spatial resolution that you're going after, the harder it is to sort of collect a global archive. There are commercial systems out there that are collecting data in the centimeter scale, tens of centimeter scale anyway. But it's very difficult to get something like a weekly global coverage from a system like that. So we kind of back off the spatial resolution in order to get that global coverage. And yeah, we bring down quite a lot of data. It's quite a volume.
So when you're building something like this, and you've recently just successfully launched Landsat 9, Do you have to, I'm thinking in terms of the archive that you already have, you have to sort of consider how the new data is going to contribute to the archive and how it's going to overlap, I guess, in a lot of ways. But do you also consider how the data you're going to be collecting is going to work in conjunction with other satellite programs out there? I'm thinking about the Copernicus Sentinels, for example.
Absolutely, we have a lot of conversations with our European colleagues about where Copernicus and the Sentinel-2 satellite program is going in the future, Sentinel-2 being the kind of closest analog within Copernicus to what Landsat does. We really do want to try to harmonize those data sets as much as possible. Our users tell us that what they really want to see is sort of a Landsat image for every part of the Earth every day. If they could snap their fingers, that's what they'd want. To actually create that, within NASA or any one space agency is extremely expensive. So we are really sort of focused on trying to use Landsat in conjunction with other systems like Sentinel-2. So that involves trying to harmonize the spectral bands as best as possible. It involves establishing some correction algorithms to worry about things like the different view angles that the sensors see any given target from. There's so many space assets, so many Earth observation systems out there now that putting them all together is really kind of the way to go.
So when I think about all of that, I think that here is a lot of decisions that need to be made before we launch this thing into space, right? So we can't correct or change a lot of the components once they're in space. I'm assuming perhaps the only thing we can really do is update the software. Can you talk to me a little bit about the components? Obviously, you need components that are going to fulfill the mission, that are going to return data based on the requirements that you have. But how do you test them? So do you try and recreate a space environment here on Earth, or do you have another way of testing these?
Yeah, that's right. So we have with Landsat a requirement for 5 years minimum mission lifetime. But actually, most of our satellites last a lot longer than that. In fact, Landsat 5, which launched in 1984, set a Guinness Book of World Record for longevity. I think it was 29 years. The way we test our satellites is we test them at the component level, at the instrument level, and then the entire observatory at once. And we do try to recreate the space environment. So we'll put them into a what we call a thermal vacuum chamber, where we cycle through the kind of hot and cold cycles they'd expect on orbit and pump out the air so that it's actually in a vacuum. We do acoustic testing, where we put massive sound waves through to simulate the launch environment. We do electromagnetic testing. So it's a whole test program at various levels of assembly to verify that the satellite's going to last as long as it has to.
Can you give me an idea of how long that this takes? So from the idea to the actual launch, what kind of time frame are we talking about?
Typically, it takes about 5, 6, 7 years to actually design and build a new satellite system. For Landsat 9, we were actually a little bit speedier because Landsat 9 is almost a copy of Landsat 8. There's some technical improvements, but kind of the zero order is that it's a rebuild of Landsat 8. So we were able to go a little bit faster. But the testing process alone, after the instruments are built and they're integrated onto the platform, that can take 6 months going on a year.
I think you mentioned that the lifespan or the expected lifespan of these satellites. You said 5 years. I can't recall that the actual number. It was something like a Guinness Book of World Records in terms of lifespan for a satellite. What determines the lifespan? Is it space is a very harsh place and things break and they get bumped around up there, or is there something else?
Well, things do break sometimes. We really try to minimize the number of moving parts on our instruments and our satellites. That's the moving part is always the Achilles heel. But the other thing that makes a difference is the fuel. So we do orbital maneuvers on a regular basis because the orbit degrades through time, and so we have to do inclination maneuvers to kind of bring it back up to the right altitude and the right equatorial crossing time. In the case of Landsat 7, which launched in 1999, and at least as of today, when we're talking, is still operating, we've used up all of our fuel for those inclination maneuvers. So the time of imaging on the Earth is actually drifting earlier and earlier, and it's starting to become not very useful scientifically. So in a lot of cases, it's actually the amount of fuel that you have that governs the lifetime of the mission.
And just so I'm clear, so what we're talking about is the gravitational pull of the Earth pulling these satellites closer and closer to Earth. And from time to time, you need to adjust that to move them back into the expected orbit so we can, take images of the world in a very predictable way. Is that correct?
Yep, there's not much drag, but there's a little bit of drag from the atmosphere, even up that high.
In an earlier conversation, you mentioned a really interesting test that I think NASA is going to be carrying out shortly. It was around refueling of a satellite. Can you talk to me about that?
Sure. So I just mentioned with Landsat 7 how we're out of fuel and we can't adjust the orbit anymore. NASA has a technology demonstration mission called OSAM-1, which is an orbital servicing mission. So the idea is to send up a robotic arm basically on a satellite along with a gas can, go up to Landsat 7, refuel the satellite and demonstrate that technology successfully. I think it's still to be determined what happens to Landsat 7 assuming that technology demonstration is successful. It's, I think, unlikely that it would be put back into service as an imaging satellite just because it's quite old already. But nevertheless, it's a pretty cool technology to be able to do that.
Absolutely, that'll be really interesting to see how that plays out. So let's say it's not being put back into service. How do you decommission a satellite?
Right. So there are some regulations. I don't know them off the top of my head. I'd have to look at the relevant rule book. But in general, a satellite has to be deorbited within a certain amount of time so that it doesn't become a hazard to people on the ground. You want to basically have a predictable reentry pattern. So typically, a certain amount of fuel is reserved at the end of the mission lifetime to actively deorbit it. That means you fire the thrusters, you slow it down, you bring it into a lower orbit, and that accelerates the reentry. And so you can monitor it over a reasonable period of time, like a few years and not, 50 years.
That's interesting. Honestly, I thought you might have used the last of the fuel and just sort of shot it off into space somewhere.
No, it takes a lot of fuel to actually get it out past Earth's orbit. So the satellites would end up being a lot bigger if you actually sent them out toward the moon or the sun or something like that. It's much easier just to bring them back into Earth.
Okay, so we got the Landsat program. You're building these satellites to help sort of further scientific work here on Earth. You figure out the kinds of data you need to collect, the spectral resolutions, the spatial resolutions. You build and test these satellites here on Earth. You shoot them off into space, and then you start collecting the data. How does the data get back to Earth?
So we have a series. Actually, it's U.S. Geological Survey now that operates the satellites once they're up. USGS operates a series of ground stations, and so it's basically microwaves that bring the data back. It's X-band transmission back to the Earth. There are about four ground receiving stations around the world which receive Landsat data and bring it back to the USGS for archive. In addition, there are a set of what we call international cooperator stations, which receive data directly from the satellite for national purposes. So these are stations in different parts of the world where they want data more rapidly and they want a direct broadcast from the satellite. So it's really that's the mechanism to bring the data down. Once they are down, then they're processed at the USGS facility in Sioux Falls, South Dakota, the Aeros Data Center.
I just want to follow up on this idea of downloading data and receiving stations. In terms of positioning, how important is that? Can they be at random positions around the world? And with the fact that the Landsat covers the globe on is it a 14-day cycle that at some stage they'll cross over one of them and you can download it, or do you have to be very careful about where these stations are, where these receiving stations are in terms of the orbit?
Sure. So the Landsat cycle is 16 days. We have a solid state recorder on each satellite, and we can accumulate kind of a day's worth of imagery on that recorder. Every time we pass over a receiving station, then we try to empty as much of the recorder as we can. It helps to have those receiving stations kind of close to the poles because all of the orbits that we're in a polar orbit. So the orbits converge toward the poles and we're in line or in sight of a receiving station more often if they're at the poles. So our primary stations are in Alaska, in Norway, South Dakota at Eros, and also there's a receiving station in Australia.
So you talked about a day's worth of data. How much data are we talking about?
So Landsat collects about 740 scenes of imagery per day, and each image might be a couple of gigabytes. So I'm not sure how that math works out, but that's that's the size.
We don't do public math on the podcast, so you're safe there.
Oh, thank you.
And just before we jump into the processing side of it, I know from conversations with people that are working in the CubeSat industry, they have this idea of tasking satellites. This might be an incredibly naive question, but is it possible to task a Landsat satellite?
Oh, yeah, we do it all the time. Every day there is a command upload that tells the satellite which images it should acquire. We don't acquire data over the open ocean, for example. It would be a waste of resources. We're a land imaging satellite, and we don't really have the radiometric sensitivity to get good data over the dark oceans. So every day there's a list of scenes, a list of locations where the satellite's going to acquire data. The other type of tasking that we do sometimes is we have the capability to roll the satellite, what we call off nadir. So generally, the satellite is looking down and just getting the images that it's flying over, but we can roll it as it's doing its orbit and get images to either side if we want to. We try not to do that very often because it eats into the core kind of routine monitoring capability that we like. But in case of natural disasters or, some sort of major event, we do have that capability.
So when you're talking about eating into the core monitoring, you're talking about leaving a hole in the archive, essentially. Is that correct?
Exactly. Yeah. And we really don't want to do that.
That makes perfect sense. We're talking about getting the data back to Earth and the processing side of things. What are we talking about when we're talking about processing Landsat data? What needs to happen to it before it becomes the images, I guess, that a lot of listeners are used to working with?
So there's really two parts of the processing you can think about. There's a geometric correction part where first of all we have to align all of the pixels that are collected by the different parts of the instrument. The instrument has different focal plane arrays, and they have to be lined up so they match geometrically. And then the second part of that is that the image has to be essentially orthorectified or draped on the surface of the Earth for geodetic accuracy. We also then do radiometric processing, and so we have to calibrate the pixels to a physical unit, which is at sensor radiance or top of atmosphere reflectance, top of atmosphere temperature in the case of the thermal bands. And so all of that processing occurs at the USGS facility. And they try as best as possible to make data products that are ready for analysis, out of the box.
So earlier in the conversation, we talked about some communication between the Landsat program and Copernicus, for example. And again, this might sound like a very naive question. Is there any sort of standard surface model that you're using when you talk about ortho-rectifying images? Because I'm assuming that the good people over at Copernicus are facing the same problem. And I'm wondering if it helps the interoperability of these data sets if they were using the same surface model.
It does, and there has been an effort to try to use the same digital terrain model for orthorectification. There are some issues associated with some of the terrain models are proprietary. They're created by commercial companies and can't necessarily be shared for free. So there's some, issues like that that get in the way. But increasingly, yes, you're absolutely right. There's a real drive to use the same Earth model for the geometric correction.
Okay, so now we've got the data back down to Earth. We've processed it. It's being archived. It's available to scientists like you. This would be a great time for you to explain to us what are scientists like you using this data for?
All right. So first, I should clarify that the data are available to anybody, and they're available for free. So you can go on to the USGS Aeros website. Earth Explorer is the website interface, and you can search by space or time or data product and download as much Landsat data to your heart's content for no cost. In terms of what the data are used for, some NASA missions are really directed to a single kind of question or scientific problem. Landsat is a Swiss Army knife. It underlays so many different kinds of analysis. So it's used in agriculture for looking at crop types, for looking at the condition of crops around the world. It's used in forestry, again, forest health, natural disturbances like insect damage and hurricanes, logging. It's used increasingly in the cryospheric community, so looking at the effects of climate change on snow and ice. There's a kind of a neat application that's emerged in the last few years where people use Landsat data taken over weeks to years to track features on glaciers and thereby derive the ice velocity. You can derive these fantastic looking ice velocity maps from Antarctica and Greenland and other places based on feature tracking from Landsat. We also use the thermal infrared channels, particularly for looking at water consumption in crops, so-called evapotranspiration. So that's how much water the crops are transpiring as part of their photosynthesis, and that's an indicator of stress. So just a whole series of applications out there for Landsat, and there are literally thousands of users who are using the data right now.
Do you see any commercial companies sort of encroaching on the same kinds of use cases, like providing the same spectral resolutions, perhaps? And yeah, I guess I can't explain it better than that, but sort of encroaching on what Landsat is trying to do, or does Landsat have a complete sort of monopoly on this kind of thing?
Sure, but I don't think I would use the word encroaching. I think more data is better. More data are better, I guess.
More data, more better, I think is the correct way of saying it.
Yeah, more data, more better, correct. I think there's a lot of synergy between what commercial companies are doing now and what Landsat can provide. Landsat does provide unique aspects. If it was completely duplicative with what commercial companies provided, then we probably wouldn't launch anymore. We just buy the data. But in fact, Landsat provides spectral coverage that most commercial companies don't provide out into the shortwave IR and again into the thermal infrared. It also provides routine global coverage and is operated essentially as a public good. Again, you can download the data for free. So those are some critical differences between Landsat and the commercial world. But as I said, I really see a lot of synergy there. People are using data from Planet or Maxar or some of the other companies in conjunction with Landsat and either using higher resolution data to train a classifier that then they operate globally on Landsat, or using the better temporal coverage from a CubeSat system to sort of fill in the gaps in Landsat time series.
Yeah, I really like the way you phrase that, more sort of synergistic. I appreciate that. Thank you. I'm sure that you mentioned the word climate change or the words climate change before when you were explaining some of the use cases for Landsat data. Oftentimes, I get really frustrated when we talk about climate change. Part of me thinks that we've got a lot of science, a lot of evidence that this is happening, and I feel like we need some more action. And that perhaps this idea of not having the perfect data or not knowing absolutely everything at the moment is almost like a distraction for us. Where is it that you think that something like Landsat can sort of help with some of the really key questions around climate change that still exist?
Yeah, right. I mean, good timing with this question, right? The UN climate discussions are going on right now as we're speaking. So Landsat has a couple of key roles. Really, the unique aspect of Landsat is being able to look at the effects of climate change on the land environment, right? So, why do we care about climate change in the first place? There's really a limited number of impacts that are going to directly affect us, and it's things like provision of food and food security, provision of fresh water, biodiversity impacts, sea level rise, and those are the areas where Landsat can sort of help us visualize what's changing on the planet. So, for example, we see areas in the high latitudes near the Arctic where we see a lot more vegetation now than we did 20 or 30 years ago in the archive. And so that's an area where warmer temperatures and longer growing seasons are having sort of a beneficial impact on vegetation. And then conversely, we see semi-arid regions in the southwestern US, for example, where we're getting increasing dieback, increasing frequency of fire. And we can use Landsat to sort of track that change in forest condition through time. And so it's really that impact of climate change on the land ecosystem that Landsat can help us pinpoint. I should also add that in addition to looking at the ecosystem impacts, as I said before, Landsat's increasingly being used by the cryospheric community to look at glacier dynamics, both the changes in the major ice sheets in Antarctica and Greenland, but also things like declining mountain glaciers around the world.
Oftentimes, when people talk about climate change, we talk about things like carbon sinks. And before, you talked a lot about vegetation. So, using Landsat to sort of figure out what is happening with the vegetation in different regions of the world. Can you talk to me a little bit about perhaps using Landsat as a way of figuring out where the carbon sinks are and perhaps how they're growing, how they're developing over time?
In terms of carbon, Landsat is our fundamental source of information for understanding the rate of tropical deforestation, which is a big source of carbon to the atmosphere. So Landsat can help us provide the area and the rate of deforestation in countries around the world. And then, in addition, there's quite a lot of carbon uptake by vegetation recovery, and so Landsat can help us look at the expansion of forests as well as areas of afforestation around the world. And so that balance between carbon loss due to deforestation and carbon gain due to afforestation is something we can look at directly.
Early in the conversation, you said something like your users would really want, if you ask them what they want, they say they want Landsat images every day of every place on the world, or something like that. It was more Landsat data, essentially. If you, as an Earth scientist, could snap your fingers, is that what you would ask for as well? More Landsat, the same, just more of it, more frequent, or is there something else?
Well, there are a set of enhancements that we're looking at for the future. So this leads into the question of what will Landsat look like in the future. The USGS and NASA have been collecting priorities from the user base from Landsat. What people say they want to see is, first of all, more frequent coverage. So that was what you were just talking about, right? So an image every day would be nice. Maybe we can't do that, but at least an image every few days. They also want to see higher spatial resolution. So the Copernicus Sentinel-2 program has really whetted people's appetite for 10-meter resolution data for routine land monitoring. For example, we know that with 30-meter spatial resolution, we miss about 30 to 40% of the fields in the developing world where they tend to be smaller size. So moving down to 10-meter resolution is really going to have some positive impact on our ability to look at food security. Finally, there's some additional spectral bands that people have identified, in particular those related to water quality. As we increase the sensitivity of Landsat and its temporal repeat, it opens up the door to start using Landsat for water quality monitoring. And so, for example, harmful algal blooms are a big concern in the US and elsewhere. There are some specific spectral bands that we can add to detect those early. So that's kind of a suite of improvements that we're really looking at for the future of Landsat right now.
So I think you mentioned early on that it takes about 5 years or something to sort of develop a satellite and get it into orbit. Can we expect to see a new Landsat satellite in 5 years' time, or is it what does the time horizon look like?
Yeah, probably not 5 years, but hopefully by around the end of the decade. That's the game plan right now. So at the moment, we're looking at Landsat Next, is what we're terming it, and we're in what we call pre-phase A studies, which is kind of NASA bureaucraties for we haven't let any contracts out, but we're looking what the requirements should be, and we're sort of doing our own internal studies on what we might be able to build. We're looking at some different kinds of architectures as well. We're looking at constellation approaches for Landsat. So instead of just putting one set of instruments on one big platform, can we kind of break this up into multiple platforms and build a little bit of resiliency into the system so you don't get that one failure that just completely takes you out?
Yeah, is this been perhaps a little bit inspired by the CubeSat industry?
Absolutely, sure. I mean, that's we're actually seeing that kind of across NASA and a lot of the science missions is a push toward smaller platforms, greater resiliency, hopefully lower cost per platform. Yeah, so that's coming out of the commercial world.
This gets back to the idea of the synergies between the public and the commercial that I think you were talking about before. And it's really interesting to hear it coming the other way as well. I guess in a lot of ways, you'll be able to take advantage of the knowledge that's already out there, in the commercial world, when you consider building these new kinds of constellations.
Yeah, that's it exactly. It would be nice to be able to put Landsat on a CubeSat and really take advantage of the lessons learned from the community that's launched fleets of CubeSats. Unfortunately, there's some physics that kind of prevents us from doing that. The spectral regions we want to collect out in the shortwave and the thermal IR, the fundamental optics are bigger than what a CubeSat can accommodate. And so we're kind of looking at that intermediate size, right? It's got to be bigger than a CubeSat, but can we shrink it down from where it is now?
Yeah, it'll be really, really interesting to see what you come up with. So this is a geospatial podcast. A lot of people listening to this are, involved in the geospatial industry in some way, shape, or form, and they're definitely engaged because they've got the time and they're interested in listening to a podcast. 30, 40 minutes of people like us talking about things like this. So we understand you. You are our people. What do you tell people when you go to a cocktail party and say, "Hey, I work at Landsat"? How do you describe what you do to them?
Well, what I try to communicate to them is sort of this amazing fact that we now have 50 years of satellite data continuously of how the planet is changing. I don't think people realize that, and I always compare it to a family photo album. You don't realize how much you and your loved ones are changing through time until you leaf back a few pages and look at the pictures from 10 or 20 years ago. And the same thing is true with the planet. And so when people ask me, what do I do? I say I'm sort of tracking the near term history of our planet and our environment. And in a way, I think that's reassuring that we have that information at our disposal at this point.
Absolutely. Jeff, thank you so much for your time. Thank you for patiently walking us through what Landsat is, how it gets to be in the sky, how it gets to be orbiting above us. Yeah, the kinds of data you're collecting, what they're being used for, and what it might look like in the future. I really appreciate your time. So there'll be people listening that are used to working with this data. For those people that aren't used to working with this data, where can they go if they want to learn more about it? Where can they go if they want to reach out or ask questions or find out more information?
Sure. So we have a couple of websites you can visit. There is a a Landsat science website that NASA Goddard hosts, where I work and that I'm connected with. But also, if you want to get a hold of the data, then you go to the USGS Earth Explorer website that I mentioned earlier. That's available from USGS Eros Research Center, and just do a Google search for Earth Explorer, and that should bring it up, and then you can order the data from there.
Thanks again for your time, Jeff. Really appreciate it.
Absolutely. Thanks for having me.
So I really hope you enjoyed that discussion with Jeff Masick, the Landsat 9 project scientist. I hope this episode provided a brief introduction to Landsat, and if you are curious and haven't worked with the data before, you can go along to earthexplorer.usgs.gov and have a look at the data for yourself, download it, use it. I think you need to log in as a user, or if you are a fan of the Spatial Temporal Asset Catalog, or STAC, there'll be a link to the STAC interface for Landsat in the show notes of this episode. So that's it for me. That's it for another episode of the Mapscaping Podcast. Thank you very much for tuning in all the way to the end. It's much appreciated. As always, you're more than welcome to reach out to me. You can find me at Mapscaping on Twitter, or there'll be a link to my LinkedIn profile in the show notes of this podcast episode. We write some pretty extensive show notes for each episode. You can find those at mapscaping.com, and I'll be back next week with a new episode. I hope that you will take the time to tune in then.